Okay, so we'll get started. This is a workshop co-hosted by Dukas and HackDuke. So my name is Laura, and this is
my name is Ivy.
So we'll be your instructors today for this workshop. I'm introducing quantum computing and Qiskit. So a little bit introduction of Dukas. Dukas stands for Duke Undergraduate Quantum Information Society, and you can find our website and you can subscribe to our mailing list. So all our events are distributed among people through our mailing list. So you'll get notification of all our events. And we are an academic-oriented student organization aiming to promote the accessibility of quantum information science and related research opportunities to more Duke undergrad. And we also have a house course that is half credit, pass and fail, offered every semester. So this workshop, an hour and 20 minutes, is basically just an extreme abbreviation of the entire semester house course. But of course, we ignore a lot of details, tons of details, and tons of other really interesting expansion and real applications. Okay, and this is our YouTube channel. So this video will be uploaded to this YouTube channel, and for our previous talk that were on Zoom, you can also find it on our YouTube channel. Okay, so today's workshop will be separated into 4 parts. So we'll begin with what is a quantum computer? What can it do? So basically just give you an feeling about how powerful it can be. And the second is we just do some actual math and of quantum computing. So what are the basic computing units? How do you build quantum circuits and how do you build quantum gates? And then we'll move on to talk about the development of the entire quantum computing industry so far, because we've learned about some basic computing units about that. And the 4th part will be a live demo on IBM's Qiskit. So Qiskit is a toolkit for you to program quantum circuits, quantum gates, and you can run it either on a simulator or on IBM's real quantum computer, their quantum devices. So that part will be pretty playful. And so let's begin with part 1. What is a quantum computer? The short answer to that is just a computer. It has the same functions and parts as a classical computer. So we'll refer to all the laptops that we are using as classical computers. So it will also have a storage. It will have compiler, it will have some quantum operating system. So it's still a computer. So it's built to solve the problems that we cannot be solved classically, and classically can be solved classically. And the quantum computers are using the laws of quantum mechanics. So what is quantum mechanics? It's a physical rule that can explain our world. So for things like atoms, molecules, and ions, they all adopt the rules of quantum mechanics, and we just use these stuff to build the quantum computer. So quantum mechanics is a mathematical framework or set of rules for the construction of physical science. And this also makes us wonder whether we can think physically about computation. As I said, if we use atoms to build our computer instead of transistors, which are much larger, we might be able to also use the power of quantum mechanics. So here is a great illustration from IBM research. So if you look at bottom left of the screen, so this F cluster, it is the most complex molecule that we can model on a world's fastest supercomputer. But this is already a really simple molecule. So if we want to develop more better drug treatment or understand our biology, we need something more powerful. So a quantum computer can do simulation like this because they are exactly built with the same rule as these molecules behave. And the reason why it is so hard to model such small molecule in classical computer is because they can be in, their quantum states can be in an enormous space. So it exceeds the power of a classical computer to model it. Here's some stats for quantum simulation. So a laptop can model a 26 electron system. A supercomputer can model a 43 electron system. And in principle, a quantum computer with 300 qubits. So qubits here is the quantum bit, like a quantum analog for a classical bit. It can perform calculations in an instant when there are atoms in the universe. So here is a quote, not an exact quote, from Richard Feynman. So quantum computer can keep up with the true complexity of nature. So he was the first man who brought up this idea of quantum simulation and a quantum computer. So besides simulation, one of the most famous problems that a quantum computer quantum algorithm can solve is factoring. So classically, it is really hard to factor a large number. So you're given a composite number and you know that two prime numbers multiplied together gives that composite number. So how do you find the two prime numbers? So if that number is 20, if that composite number is 21, we know obviously it's 3 times 7. But if we are given only 4 digits, 5,207, I forgot the answer. So I don't know what are the two prime numbers that they give. But basically, all the classical algorithms that we have are just doing guess and check. So the running time for these algorithms are just all exponential. But classically, there's this really famous Shor's algorithms that can solve this problem in polynomial time. So there's an exponential speedup in factoring large numbers. And why factoring a large number is so important is because current encryption schemes relies hugely a lot, at least on the hardness of factoring. So RSA encryption is an encryption scheme that is widely used in bank services. So why it is important? Because so let's say I want to transmit some information to Aining, and I want only her can know the information what it is. So you guys won't know what I'm passing to her. So what we'll do is that Aining will generate 2 prime numbers, X and Y. They're usually really long, like 1,000 bits of 1,000 bits. So X and Y, they're prime number. And she will multiply these 2 prime numbers together and make it the public key. So the public key is something all of us know. So we know the composite number, but we don't know what the X and Y are. So X will be a private key. So what I will do is that I'll encrypt my message using the public key, and I'll send to Aining. So if some of you get the message, you couldn't interpret it because you don't have the private key, and only Aining has a private key. So this is why we're saying that RSA encryption relies on the hardness of factoring, because even if we have the public key, like none of you will know the private key unless you actually have it, you're given the private key. So you may be wondering, so a quantum computer can break this RSA encryption in 8 hours. And this encryption should be guaranteed to store data securely for 25 years. This sounds really scary since it's so powerful, but at the same time, post-quantum cryptography is also being developed, meaning that some people are also developing anti-strategy to this kind of quantum cryptography at the same time. So we don't need to really worry about it. So a third application that is super important is search. So how do we usually sort, like search an unsorted list classically? If that is unsorted, we just need to check each of the items, individual items n times. But with the Groove's algorithm, is a quantum algorithm, you can search a list with square root over n steps. So this is a quadratic speedup. It is not as good as the exponential speedup, but it is still pretty nice. And one of the importance about the search algorithm is that any problem in computer science can be modeled as search, like optimization problem, planning, gameplay, etc. And here's a little summary about NP problems in quantum computing. So this part, like NP problems, NP complete P problems, are how we classically categorize the complex, like how complex they are. And BQP is the area where quantum algorithms lie in. So it's a class of problems on a quantum computer can solve in polynomial time with bounded errors. And so you can see you can solve some NP problems, and you can solve some problems that is outside of NP, and you can solve all the obviously P problems. Okay, so before that, do we have any questions so far? Yes?
What is outside of NP?
Outside of NP, actually, I'm not quite sure.
Okay.
Okay. Yeah. Okay.
Can you explain how
We'll get in. So very higher level idea. Every step in groups algorithms can able to make the probability of finding this result higher. So it will make this blue or purple blocks with a higher probability of appearing. So when you measure it in the end, you'll have a higher probability of finding it. So it will amplify its amplitude. Okay. Okay, some exciting stuff. How did we actually do quantum computing? So the overview for this part, we'll start with the really famous double slit experiment, just to give you a intuition about how quantum mechanics work and how weird it is. And then we'll talk about quantum qubits, quantum states, which are analog to bits, classical bits. So we'll include three really famous ideas, concepts that you've may heard before: superposition, measurement, and entanglement. Part will be an introduction on quantum circuits and quantum gates. So, and these are all like circuits and gates, something you already know classically. So double slit experiment. So what is the setup for it? We've got an electron beam that is shooting electrons to go through the two small slits and finally arrive at the screen. So the screen will tell us where its final locations are on the screen. So this is really simple. And if electron is wave, we will like light or water waves. So we'll actually, when it goes through, after it goes through the double slit, we'll actually see two waves interfering with each other. So we'll see the interference pattern on the screen. And if electron is particle, like concrete little stones, we can actually see them following with two peaks, so two Gaussian. So what we actually see. Interestingly, we thought the electrons should be particle, but actually we see interference patterns. So yeah, we actually see interference pattern, which means that electrons are wave. Even more surprisingly, even if we shot the electron one by one, we can still see the interference pattern. So we thought the electron will either go to one of the slits so it won't interfere with each other, but it turns out that they interfere with itself, and then we can still see the interference pattern. So this is really interesting. So which also proves that the electron is wave, so interferes itself. What about we put a detector at the double slit to actually see which slit the particle goes through? So we also shot the electron one by one and record which slit they go through. And it turns out that we see two peaks. Turns out that the electrons are particle again. And scientists are really confused. We're really confused at the beginning. So what they did is that they're trying to see if the electron can feel that there's a detector. So they put a detector at the double slit, but they unplug it. They unplug, so it's not actually a working detector. It just put a detector there, and it turns out to be interference pattern. So it seems that the electron really know whether it is being observed. So they change the behavior accordingly. And this is what is known as the wave-particle duality of electron. And yes, so what can we learn from this experiment is that the measurement and observation will change the quantum states of particle. And we'll talk about more why this results look like interference pattern later. So this double slit experiment, just to give you a sense of how weird quantum mechanics is and why an electron can be a wave or particle at the same time. Okay. So we'll talk about bit and qubit. So classically, a bit is a binary digit of 0 and 1. So 0 is off and 1 is on. They're built using transistors. And quantumly, a qubit can be a 0 or a 1, or literally both. So a little notation here. So to make it different from the classical bit, we will use a cat, like a cat. It's called cat, to separate it from the classical 0 and 1. So we have cat 0 and cat 1. So these are quantum states. And when we would say that both, it means that it is a superposition of 0 and 1. So it can be in a 0 state and a 1 state. So it's the same as Schrodinger's cat being alive and being dead at the same time. And these qubits can be represented using electrons, photons, atoms, or something you may have heard like superconducting qubits. And let us expand into what these cat 0 and cat 1 really are. So each qubit, like remember, a single qubit is actually a two-dimensional complex vector of length 1. And the cat 0 and cat 1 is something we call the computational basis state. So it's just a unit vector where one of the position is a 1. And an arbitrary qubit is typically written as this cat phi. And this alpha 0 plus beta 1 is a linear combination of the computational basis. And it is also normalized, which means that the alpha and beta are called their amplitude, and your amplitude square to the square plus together is just 1. So the length of this complex vector is 1. And this block sphere is a really nice visualization of how we can perceive qubit. How we can perceive qubit. So we can actually find a 1-to-1 correspondence between every qubit and the point on the surface of the block sphere. So every qubit is a point on the surface of the block sphere, and the block sphere has radius 1, so they are normalized. So one question you may wonder is that, so alpha and beta are complex numbers, so there should be 4 degrees of freedom. So each complex number has a real part and a complex part. But the surface has 2 degrees of freedom. So how does it coincide with each other? How could the mapping be 1-to-1? This is because we have this normalization that is 1. So we remove 1 degree of freedom, and then we remove a global phase. So for example, if we have cat 0 and e to the I cat 0. So we redeem them as the same thing because it's just a global phase. It's a coefficient in front of the entire vector. So we just ignore another degree of freedom. So we can map every arbitrary qubit to a point on the surface of the block sphere. And so what does a superposition actually look like? Then it comes to the idea of measurement. So measuring a superposition actually collapses a superposition state into 0 or 1 probabilistically. So if we measure the qubit phi, and the result of getting 0 state will be alpha squared. Probability of getting a 1 state will be beta squared. So because of the normalization, this probability holds because they sum up to 1. And decoherence is the idea that environment accidentally measuring a qubit. So one of the problems that happens in a lot of quantum devices that decoherence just happens all the time. So if you don't want to measure it, but the environment accidentally measure it, your state are entirely destroyed. So all the information you stored in it will be gone. So now we can think about when we put a detector at the double slit. So this is the same setting as the double slit experiment. So electric on, double slit and measure at a screen. So if we don't measure it, we will receive phi, and then the phi will just be safely arrived at the measured screen. So it will still be phi. But if we have a detector, then this phi will collapse into slit 1 or slit 0 with equal probability because we measure it and then we force the electron to choose a way to go instead of staying in the superposition state. So when it arrives at the screen, we will just be either slit 0 or slit 1, but not a superposition state. Do we have any questions so far? Okay. So now we can move on to build our quantum circuits. So what we know as quantum states and quantum bits are what is after the initialization. So we'll start with some really basic quantum states and we prepare them to be ready as some fancier states, fancier starting state. And then we can apply a series of quantum gates to evolve these states. And then in the end, we will measure the qubits because what we get in the end are classical results. So we want to use quantum algorithms to solve classical problems, and the classical problems will be in just number, not quantum states. And so classically, for a single bit, 0 or 1, there's only one thing you can do it, is just to flip it. So you flip a 0 to a 1, you flip a 1 to a 0. But there are many things you can do with a qubit. This is because, remember, as we said, every point on the surface of the block sphere corresponds to a qubit. So actually, all one qubit operations are just rotations on a block sphere. So on this block sphere, its north pole is the cat 0 state, and the south pole is the cat 1 state, and just rotated around the surface. And general quantum states are represented using unitary matrices. So unitary matrices are something, mathematically speaking, if you this U star is the complex transpose. So if you multiply the complex transpose with itself, you get a 1. It means that these are unitary matrices. And what is important about them, I think, is that when you apply unitary matrices to a length 1 vector, you still got a length 1 vector. So unitary matrices preserve the length of vectors, and so that if we apply a quantum gate to a quantum state, we're guaranteed that the result will still be a valid quantum state. So this is why we choose unitary matrices to represent quantum operations. And here's some really important 1 qubit gates. So poly X and poly Z, they are all of 2 by 2 dimension unitary matrices. You can verify them. So let's see what, like when we apply poly X to quantum states. So if we apply X, this matrix, to the cat 0, which is 1, 0, you will actually get 0, 1. So you kind of flip it. And if you apply X to 1, you will also flip it. So we call this a bit flip operation. And same thing with Z. So it won't do anything when you apply Z to 0, but it will make 1 into a -1 if you apply it only to 1. So it's called a phase flip operation. So you flip the face of the cat 1 state. And another really important 1 qubit gate is called Hadamard gate. it can be used to create superposition. So if we apply h to 0, ignore the calculation, and what you get is this superposition of 0 and 1 state. And this square root of 2 is just a normalization factor, so that the length of it is still 1. So it's a superposition. And if we apply it to 1, you'll get this state. So if we see it on the block sphere, so we start from 0 state, and the Hadamard gate will rotate it to the positive x direction. And when we evolve to multiple qubits, we use tensor product to tensor them together. So this AB can be the first qubit, and CD can be the second qubit, and the resulting vector is actually of dimension 4, but still length 1. Let us put the example in a computational basis. So 10 tensor 10 will be another unit vector where the first position is a 1. So this is the first, also the first two-dimensional qubit. And if we apply a 0, 1, we will get another unit vector where the second position is a 1. So it's 0, 1. So you just can ignore this tensor product and just put the two zeros together. But remember, two qubits can be one of these 4 states, or they can be any of the states that is the linear combination of them, so a superposition state. And the Hadamard gate can be used to create a superposition of these 4 states. So this Hadamard tensor to the 2 is just you put Hadamard gate to the first qubit and you put Hadamard gate to the second qubit. So you'll produce something like this. And you may notice that this scales exponentially with the number of qubits. So if you got n qubit, then the length, the vector, your dimension of your space will be 2 to the n. So it is an enormous quantum state that you can live in. So this is also one of the reasons why quantum computer can be so powerful, because it can harness such a big space and such computational power. And some examples of qubit states. So tensor product states, which is the most basic, you just apply these gate individually on qubits. And so this C0 gate is called control not. It applies on one qubit called control, another qubit called target. So it will flip the target qubit if and only if the control is a 1. So we've got the control and the target. So let's see. So the first qubit is control. So it won't do anything to target. It will just preserve the entire states. And if the control bit is a 1, so it will flip the target from 0 to 1 and flip 1 to a 0. So, and you can also verify that the matrix representation of this C0 gate is actually still unitary. Okay, so now let's move on to the really interesting idea of entanglement. So what entanglement is saying that if we got 2 qubits that are entangled together, and we separate them long distance away from each other, and if we measure 1 qubit, we'll instantaneously know what the other qubit will be. So let us take this 0, 0 plus 1, 1 state with normalization factor as an example. So we got 2 qubits that are in this state, and then we separate them all far away from each other. And if we measure the first qubit that is 0, then we immediately know that the second qubit must be 0, because the only quantum states that they can be in is either 0, 0 or 1, 1. So there's a correlation between these 2 qubits, and then they seem to know each other really well. And no matter how long distance they're away from each other, they still have this magical entangled effects. And this instantaneous thing just literally means instantaneous. So it has nothing to do with the speed of light. You cannot exceed it, things like that. So Einstein didn't agree with it at all. He was saying that I cannot seriously believe in in it because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky actions at a distance. So he's calling this spooky actions at a distance. And also because this spooky actions ignores locality. So who would win? One of the greatest physicists to ever live, or some spooky boys? Well, Einstein's was wrong. Has been experimentally proved that the entanglement actually exists. And some theory that for you to understand is just this two qubit state, 0, 0 plus 1, 1 over square root of 2. Okay, so how can we produce this entangled state? So our ingredients will just be the Hadamard gate and the CNOT gate, which we just learned. So what we should do is to make the control to the CNOT gate a superposition state. So there's a difference between superposition and entanglement, just to remind you of that. So this is a setting of our quantum circuit. So we first apply a Hadamard gate on 0. So remember, this will produce a superposition state exactly like this, 0 plus 1 over square root of 2. And then we apply a CNOT gate so that our control is this state. And so this initial state is 0, 0. And then we make it this superposition state tensor a 0 state, which does not got changed at all. And then we apply it to a CNOT gate, and in the end, we will produce a entangled state. We'll see this entanglement again later in the Qiskit demo. So this is a really simple application of something we can do. It's called teleportation, which means that we teleport a qubit. Yeah, we teleport a qubit. And this is a new thing that in 2017, researchers in China have teleported a photon from the ground to a satellite orbiting more than 500 kilometers above. So it's the first object teleported from Earth to orbit with using only this simple circuit. I mean, this is definitely a higher level abstract idea of how the circuit actually performs. There are also tons of nasty details about the actual implementation of how to preserve your fidelity, how to make these gates perform well without errors. So a little bit recap of second part. So we learned about quantum states, and one qubit is a two-dimensional complex vector of length 1, and qubits can be in superposition of like a linear combination of these kit 0 and kit 1. And measurement will destroy the states. It will force it to be either 0 or either 1. And the entanglements is just kind of spooky effects at very long distance. And then we learned about quantum gates. Quantum states have 3 stages where you first prepare your states, quantum state, and then you evolve them, and in the end you measure them to get classical measurement results. So we give some example of 1 qubit gates like poly X and Z and Hadamard gate. We give some examples of 2 qubit gates like control NOT, and then we mentioned how can we use Hadamard gate to create superposition, and then how can we use this created superposition state to create entangled states with combined with control NOT. So do we have any questions before we move on to development of quantum computing industry? Yes?
Question about entanglement. What typically causes 2 qubits? What causes them to be?
If we're talking about physics, then I have to say I don't know. But if you're thinking it in a higher level, so all the quantum gates, so qubits are like atoms, ions, and the quantum gates are actions on them. So you perform, for example, you can perform lasers on them. So in terms of the real physics, I don't really know, but if you think of there's something and then you have a laser putting on it, and then it do some kind of and then evolves. But so all the quantum operations can be think of in that way. And then if you have two qubit gates, and then you perform it on two qubits together, that will produce something that entangle this together, because that is a two qubit gates. Yes, and mathematically, it tells us that is true. We will produce something that is entangled together. So the reason why I like quantum mechanics so much is because, as I said at the beginning, it is a mathematical framework that tell us about the rules of how those little things behave. And they are so true. So they just act so concurrently in this linear algebra formalism. Yeah, but about the physics, I don't know. Sorry.
No, it's okay.
Yeah.
So to recap, it's an operation applied to one. No.
Yes, yes, this is what I think. Yes. Any more questions?
Question.
Uh-huh.
I was going to ask more about Hadamard data.
Yes.
Clarifying it a little bit. It seems to be very simple, but I'm not quite sure that I understand.
Okay. For now, you can know that you can just think of it as a quantum gate, but we can talk more after this workshop. Okay, because it's getting to nasty details. Any? Okay, so yeah, so I'll start talking about like the development of quantum computing industry. So just some knowledge. So today IBM actually has a roadmap of the next about like 20 years of like what they want quantum computers to be. And then actually in 2019, they've announced that they have a quantum computer with 65 qubits, I believe. And in their plan, they want to achieve 127 qubits this year, and then larger than 1,000, more than 1,000 qubits next year. So yeah, so you can see that the number of qubits in the quantum computer is growing exponentially. But although like the growth is very fast, there are also some challenges. The first one is Cubist stability. So basically qubits are very fragile and it's very prone to errors. And developers want qubits that are as reliable and as the bit in an ordinary computer, and that's not easy. Google, IBM, and like use qubits made of tiny resonating circuit of superconducting metal etches into microchips. Yeah, and which so far have like it's easier to control and integrate into circuit than other types of qubits. And so in summary, how do we improve the computational power of a quantum computer? The intuition is that we want as much storing space that are accurate as possible. So there are two ways essentially to improve the computational power of a quantum computer. The first one is to improve the number of qubits in a quantum computer, and the second one is to improve their accuracy. In the race of building quantum computers, actually different companies, different institutions have their different approaches. And we will only have like right here is two approaches that different companies have. And the first one, actually the second one is used by Duke. And many professors at Duke conduct research in trapped ions. And if you're interested, you can reach out to them and like ask about their research. Yeah, so that is a brief overview of the development of quantum computation. Yeah.
I want to add that the trapped ion, as Aini said, is what technology that Duke is using. And Duke has two professors who founded a company called IonQ, which was the first quantum startup company that went public in October. So you can actually buy their stocks. And they use trapped ion because it has really high stability. If you can see from the proof, it's very stable compared with superconducting qubits, but it just is the cost is slow. But I personally feel like for current stages, like stability is really important. And IonQ going public also means that the industry has a lot of hope in the trap ion technology as well.
Yeah, and adding on that, I think right now superconducting loops are the most popular, but
Yes.
yeah,
But the reason why they're popular is because current industry relies a lot on the maturity of superconducting technology. So we've got years of development already in superconducting technology. So these large companies like Google, IBM, they just have the advantage of using them. Yes.
What is the longevity? It's a higher longevity, better.
I'm not a physics.
Right.
Yeah,
None of us physics major.
yeah, no, but
I think the longevity means that how long your quantum state can preserve. Yeah. Stable. I think so.
Yeah.
In terms of longevity, stability.
Definitely does know what caused that problem.
Incoherence. It definitely does. But I don't know the specific.
yeah. Yeah, so right now, we can go into the details of how to actually build a quantum circuit and run it on a actually quantum computer. So before I go into this part, I just want to introduce like this GitHub link, which has all the previous demos that we had on our house course. And what I'm gonna demo today is like a very simple version of Quantum Hello World. And for those of you who have maybe advanced program experience, it might be too easy, but you can, like, after you get the idea, you can check out like advanced algorithms like Shor's algorithm and everything on this page, and yeah, maybe learn about more algorithms. So yeah, let's get started. So first, I'll give like a brief introduction to Qiskit. So what is Qiskit? It is an open source software development kit for working with quantum computers. It provides tools to create quantum programs and run them on IBM's cloud quantum computing service, or on simulators on a local computer. So you can build circuits, you can run it on actual quantum computers, and you can run it on simulators. And speaking of the framework of Qiskit, it is actually made up of elements that serve different purposes. So for example, it has like Qiskit Terra, which is tools to create quantum circuits at or close to the level of quantum machine code. And Qiskit Air is a high performance quantum computer simulator with realistic noise models. You can see that down there, there are a lot of interesting components. For example, Qiskit optimization, Qiskit machine learning. They are still in the development stage, which means that the packages inside these components are not like as developed as packages like sklearn or like what we say in classical machine learning, but it is open source, so you can develop it if you want. And another resource is the Qiskit textbook. If you click into this link, yeah, so this is the Qiskit textbook, and it's a free digital textbook that will teach you the mathematics behind quantum algorithms, and the details about today's quantum hardware, and writing code in Qiskit. Yeah, so you can see that it's very detailed. It has quantum algorithm for applications, and it has like some hardware investigation and measurements with Qiskit. So if you're interested after this workshop, you can read it and yeah, get to know more about it. So, okay. Right now, let's go into the details of how to install Qiskit. The first thing we need to do is to install Anaconda. And I assume like most of you know Anaconda, and in case you don't know, it's just like a data science toolkit. It provides a lot of packages for scientific computing, NumPy panels, and like packages for machine learning. You can install it with this link. And after you've installed Anaconda, you need to install Qiskit. So you either open your terminal in Mac or Linux or open the Anaconda prompt in Windows and run pip install Qiskit, and that's all you need to install Qiskit. So I have to mention that Anaconda is not necessary for installing Qiskit, but I recommend using it because it is the easiest way for you to start programming quantum circuits without worrying about the package dependencies. And after we installed Qiskit, we'll actually use Jupyter Notebook. And just a brief introduction to Jupyter Notebook. It is a web application that allows you to create and share documents that contain live code, equations, visualizations, and narrative text. So you can see this is a screenshot of Jupyter Notebook, and you can write markdown text, you can write executable Python code, and you can generate visualizations with Python packages. And let's start our live demo right now. So I'll just first open Jupyter Notebook in my terminal, Anaconda terminal. So, okay, let's type Jupyter Notebook. Right. And this is what it looks like to after you open the Jupyter Notebook. And let's just first create a new notebook under Python 3. And we'll name it Quantum Hello World. And the first thing you want to do after you install Qiskit is probably to check that whether Qiskit is installed correctly. So you want to type import Qiskit and hit Shift Enter. Is it better now? Yeah, so as you see, there's no errors, and that means you've installed Qiskit correctly. And before we start actually building a circuit, another thing I want to mention is that in order to run your quantum circuit on the IBM quantum computer, you need a permission code for that. So you need to go to this link, quantumcomputing.ibm.com, and then you need to create a new account. And after creating that new account, you can see from the homepage that you have, there's your API token right there, and you need to load this API token into Qiskit so that you can actually access a computational resource at IBM. And right, so. And this is my page, and you can see that my API token is here. And right, and let's start programming. And the first thing I want to do is just maybe load my token into Qiskit. So from Qiskit import IBMQ, and then IBMQ dot load account. And then you just want to copy your API token right here. I hope it's, and then because I need to override it, and let's just run this. It might take a second, so let's just do the following when it is running. And IBMQ dot load account, just to check that the account is loaded correctly. Sorry. Save account here, and then here. Let's do it again, and load account, right? And right now the account is loaded, and you can see that your hub, your group, and your project, which we will be using later. So yeah, so right now let's really start creating a quantum circuit. So first we want to import everything from Qiskit, import star. And then first let's we'll create a circuit with 2 quantum bits and 2 classical bits. So let's first create our 2 quantum bits, quantum register. And just in case if you don't know what a register is, it is just like a programming unit that stores the information inside. So just like classical computers have registers, quantum computers have quantum registers. And then let's create 2 classical registers. Classical register 2. And then let's create a circuit with these registers. Circuit QR and pass in the 2 registers we've created. Did I spell anything wrong? Yeah, sorry. And yeah, and right now we've created our circuit. And another thing is that because we're using Python, we can use all the drawing packages in Python. So let's just see what our circuit look like right now. So circuit dot draw and execute it. So right now we created a circuit and it has 2 quantum bits, QR sub 0, Q2 sub 0, Q2 sub 1, and then 2 classical bits right there. And right now, okay, so right now we want to actually apply gates on this circuit. And the first thing we want to do is we want to create entanglements between the 2 quantum bits, right? And the first thing, as Nora just talked about before, the first thing we want to do is just we want to apply a Hadamard gate on the first qubit. So the way circuit circuit.h so .h is just how you provide how you give like a Hadamard gate on the first qubit. And then we want to draw the circuit. And we just to make it more beautiful, we maybe want to use MPL. Right. So if you see the H right there, that is when you provide like you get a Hadamard gate on the first qubit. And then remember the second thing we want to do in the entanglement is just we want to apply a CNOT gate of when the first qubit is the control and the second one is the target. So let's just give a CNOT gate here. .cx. So CX stands for CNOT, and we want to first so the first one is the control bit and the second one is the target bit. And then we still want to draw a circuit. Draw output. Right. So right now we've like had like a CNOT gate as for the first one to be the control and the second one to be the target. And so right now actually the circuit is we've built the circuit, but right now we don't know the result of the circuit, right? And how do we know the result of a quantum circuit is that we need to measure the quantum bits, and that's why we need the classical bits. So right now we want to store the measuring results of the 2 quantum bits into the 2 classical bits. And let's just write circuit dot measure QR/CR, which just measures the qubit and stores it in the classical bit. And right now raw output equals so the 2 figures right there is just symboling that we are measuring the 2 qubits and putting it in the classical bit. And so what is the result? We need to print it, right? So so the way to print it is just first we want to run it on the simulator on our local computer. So we first need to initialize the simulator. Simulator equals, and we're using the air simulator, which is a component in Qiskit. Get backend quantum simulator. And then we want to execute. So we want to execute the quantum circuit and then put the results in the result variable. Execute circuit backend equals simulator dot result. Right. So right now we've executed and we've stored the results into the result variable. And now let's just visualize the result. So we want to first implement, so just import like a visualization tool. Visualization import plot histogram. And after that, we want to put the result into the histogram. So plot histogram result dot get counts. Get counts. Right. Okay, so right now we've let me zoom out this. So right now we've measured the quantum circuit, and we can see that the only result of the quantum circuit is 0, 0, and 1, 1, and that's how we create an entanglement, right? Just like from a mathematical perspective. So why does this gives us an entanglement? Because whenever you measure one qubit, for example, is 0, the other one has to be 0, right? It cannot be 1, because there's no probability that that you can measure 0, 1 from it, right? And that's how we create entanglement, because if the first one is 0, the second one must be 0, and if the first one is 1, the second one must be 1, right? Okay, and so right now we've show the result in the simulator, and right now we are very confident that our quantum circuit works, right? And we want to upload it to the computational resource on IBM, and then run it on the IBM cloud. So first, actually I'm not going to type this. So to run it on the IBM cloud, the first thing to do is to just initialize the provider, and what we put in here is just the result that you had from your load account execution. So you can see that hub equals IBM.Q and everything. And then the computer you want to use, and here is just the name of the computer you want to use. And there's actually many names. And right now we're using the quantum computer in San Diego. And we initialize the job and then put it in the job monitor. So the idea is that in the IBM computer, there's actually a queue of jobs they're executing. So people are uploading their quantum computers from everywhere around the world. And you need to stay in the queue to wait for the computer to execute your code. And after you've put the job state here, and it says the job has successfully run, you can put the result in the result variable and then visualize it. So right now, we can see that this histogram is actually a little different from the previous one, right? And the difference here is that not only it has results 0, 0, and 1, 1, it also has the results 0, 1, and 1, 0. So why is that? So supposedly entanglement will generate only 0, 0, and 1, 1. But why does the real quantum computer generate 0, 1, and 1, 0? Anyone has any guess on why is it? Is it incorrect or anything? Yeah, so this actually has to do with what we call like what we said previously on the slide, like that the qubits are very fragile right now and is very prone to errors. So the simulation has some error simulating in their code, but it is not that good. So it didn't simulate the error here, but you can see right now that our qubits, our quantum computer is not that accurate. Even in this very simple circuit, there will be errors, and the entanglement is not perfect. So we need to keep improving the measurement error of our quantum computers to get more accurate results. And that's our Hello World program. Right. And I think that's all of my part. Yeah. just click on that link. Yeah, just another tour on the Qiskit textbook. So first of all, there's a lot of introductions, and actually let me find the. Okay. So actually, first it has everything that we've been through today. So all the gates and like how does it work in mathematics. So you can actually look at it, and then right here, there's a lot of algorithms explained in depth. For example, Gruber's algorithm, as someone mentioned before, and there's actually like a very, so you can read about it, and there's source algorithm right here that decomposes prime numbers, and also you can investigate on quantum hardware using the circuit. So what we did before is actually kind of investigating on the hardware because we find that it is very prone to errors, but there's also other ways that you can measure the hardware, and it is introduced here.
Yeah, so IBM has actually devoted a lot of effort into building this community. So they wrote this Qiskit textbook that includes so many applications. If you go down to below, there's actually some quantum error correction schemes. And they've also included quantum machine learning, I believe. And so Shor's algorithm and Gruber's algorithm are just basic textbook examples. Even though they're really important, of course, but they're still like textbook examples. But Qiskit textbook has included many other interesting examples that you may find interesting also in your active project. So you can look into that. They also have a quantum neural network hybrid quantum classical neural network.
With PyTorch
Yes.
and Qiskit.
And it's pretty cool. So you can look
Basically,
into
you
that.
build a CNN.
Yeah. So IBM, they also have a community where you ask questions and they have all their 24/7 to answer your questions. They also encourage people to answer each other's questions on Qiskit so that they can better develop this toolkit. Yep, I think.
Yes. Yeah, I think that's it. Yeah. Okay. Do we have any questions? Anyone are going to have to next week? Okay.
I was gonna
Looking
ask,
forward to that.
in years past, have there been any projects done?
No, this is the first year. Yes, because Qubit was founded in 2020, but it was during the pandemic, so